Hi everyone. Today it's our first look at Hess's Law proper. The formula for Hess's Law can be a little bit intimidating at first. It looks pretty fancy, but in the end I think we'll find that it's not so bad. What is it trying to tell us? It's trying to tell us that delta H, the enthalpy change, this funny symbol at the start, that's a capital Greek sigma. It means the sum of. So it says, the sum of the moles, N, multiplied by the standard molar enthalpy of formation of the products, subtract the sum of the moles times the molar enthalpy of formation of the reactants. All these moles are always our coefficients. They're always the balancing numbers of our balanced chemical reaction. And this HF, this little circle means it's standardized. H is molar enthalpy, and here the F, molar enthalpy of formation. These values we can find in the data booklet on page 4 and 5, on a couple pages very clearly labeled standard molar enthalpies of formation. Heads up, elements do not have a molar enthalpy of formation. They do not undergo formation reactions. They're not even listed at all in the data book. 0 for them. Also, we're going to have to really pay attention to the state of our water. We're going to expect to have water vapor when we encounter hydrocarbon combustion. However, if we get told that the combustion's taking place in a closed system, for example, in a bomb calorimeter, we're actually going to get liquid water in that case. That's important because in the data booklet, all of these compounds are only listed one time except water, which is listed twice. There's a different value for water vapor contrasted with liquid water. It's not going to happen very often that we encounter liquid water, but we need to be prepared just in case. I have a balanced chemical reaction set up over here, a reaction between zinc sulfide and oxygen. I'm being asked, what's the delta H? I'm really going to build up to Hess's law in a slightly drawn out way, in a very explicit way, hopefully. Okay, so the first thing to notice is we have to do the products subtract the reactants. Just a reminder, the products are the chemicals that come after the arrow, and the reactants on the left-hand side. So I color-coded it to match. Each chemical in a reaction has an N and an HF. Every chemical has an N, a coefficient. There's a number balancing each chemical. That coefficient might be a 1. We might not explicitly be able to see the digit 1, but there's always some sort of balancing coefficient. It might even be a decimal. And these HFs, standard molar enthalpy of formation, we can find them in the data booklet. So our zinc sulfide, it has a balancing number N2, and it has a molar enthalpy of formation that I can look up in the data booklet. Same with the oxygen, it has a coefficient, it has a heat of formation. Reminder, elements are 0. Sure, oxygen is diatomic, that's the elemental form of oxygen. Our zinc oxide product, it has a coefficient, and I can look up its heat of formation. The sulfur dioxide at the back likewise has a balancing number, a coefficient, an N, and a molar enthalpy of formation that I could look up in the data book. Let's look again at the formula. It's the sum of the NHF of the products. The sum of them. The NHF of the products added together. It's the sum of the products subtract the sum of the moles times the molar enthalpy of formation of the reactants. So we're going to have these two added together, subtract these reactants. Okay? I'm going to change that into the form that we're experiencing in the equation. Delta H equals. I like to just put a big square bracket. At first, we have to start with the products. NHF. We have our 2 moles for the zinc oxide balanced with the 2. I go into my data booklet. I look up zinc sulfide. Zinc oxide, zinc oxide, the product. Zinc oxide, negative 350.5 kilojoules per mole. Plus, this sulfur dioxide is also balanced with the 2. And now I'm going to look up SO2, sulfur dioxide. Sulfur dioxide, negative 296.8 kilojoules per mole. That's the sum of the moles times the molar enthalpy of formation of the products. The zinc oxide, the sulfur dioxide. Then there's this big subtraction in the middle right there. Subtract. I'm going to do the same thing now for the reactants. I have my zinc sulfide balanced with a 2. Two moles. And I look up in the data booklet, zinc sulfide, negative 206.0 kilojoules per mole. And I add the oxygen balanced with a 3, but then a 0 for the molar enthalpy of formation. It's takes a bit of space to write all that down, but the good news is, if I'm careful with my calculator, I can punch it all in one step. Okay? Before I do that, let's just double check where the numbers came from. The products come first. The sum of, I'm going to add them together. The NHF of the products, both of them added together. Now there might be 3 chemicals there might only be 1. This one happened to have 2. There I am, I'm adding together. This 2 and negative 350 comes from the zinc oxide. This 2 and the negative 296 comes from the sulfur dioxide. I have a big subtraction right in the middle of my calculation, and I'm doing the same thing for the reactants on the back half of the calculation. We have our zinc sulfide, our 3 oxygens multiplied by 0 because for elements, the standard molar enthalpy of formation is 0. Now I'm just going to type all this into my calculator in one step. I'm going to still use an extra set of brackets for these big square ones. Here we go. 2 negative 350.5 plus 2 negative 296.8 subtract 2 negative 206. I really need to be careful with my calculator. Okay? The answer that I got, negative 882.6 kilojoules. Now, the coefficients were counted. They're not a measured value, 2, 3, 2, 2. So because they're counted and not a measured quantity, they do not affect our significant digits. And our molar enthalpies of formation, they are standardized. That's what that little circle means. They're standardized. So that means they're official. So they're also separate from any thoughts about significant digits. So when we do Hess's law using counted coefficients or standardized values, whatever number comes up on our calculator, we don't have to round it or do anything. Significant digits are not part of this. And the units are kilojoules, just like we would expect for our other enthalpy changes. Really watch your pluses and minuses as you're writing it down, as you're calculating. And don't forget to do products minus reactants. A really common mistake is to have those flip-flopped. And I hope that helps.